Okay, so let's get started with quiz 7. As I said earlier, I don't know if some of you might not have been there in last few classes, but here is an important sort of post that I made that you want to be aware of. So these are the general topics that we covered during the exam or during the second half of this course. And so I have listed out all the topics, and within the topic I have listed out the subtopics that we kind of looked at. So make sure that you understand or you know answers to these questions. Okay, I'm not saying that these will be the questions that will come on the exam, but this is sort of the general understanding that you want to have uh, apart from sort of practicing the gradients quizzes. All right. Okay, so let's start with the first quiz, and I'll judge by your response. If you are okay, I'll just move fast. Otherwise, I'll spend a little more time. Right. So the first question here is about linear regression. Right. So the idea here, the thing that you want to know is what is linear regression, right? So linear regression, there is notion of an x and y. X are your inputs, y is your output, and the way they are connected in linear regression is y is equal to w transpose x, right? And typically we also include a bias, right? So you can look up the discussion that we had, but there is a notion of adding a bias term which helps you with the intercept of the line, right? So without the bias, and this is something that you would have seen in your programming assignment 2 as well, that if you don't have the bias, then the results are typically poor because you are forcing your line or your plane that you're fitting to go through to pass through the origin, right? Which, you know, the data might not like that, right? So that's why we include the bias, and I hope you know how to include the bias, just adding one more constant term on to your x, appending another column, right? And then, so that is one general discussion. Then I hope you also know how to learn the weights, right? So there's a direct minimization that we sort of derived, which is you're trying to minimize the squared error on your training data, or you are trying to maximize the maximum likelihood, depending on if you are doing sort of error minimization or the Bayesian sort of regression. But in both cases, you get to the same answer, right? So you want to know what the formula is and how do we do that steps to that derivation, right? The other important thing with sort of linear regression that you need to understand is this notion of basis function expansion, right? So why do we do that? That's number one. The answer for that is because sometimes a line might not be enough. You want to learn a non-linear sort of a curve, because that might fit the data more, right? So if this is your simple linear regression setting, this is your x and this is your y, and this is your training data, and let's say these are your data points, right? So if you just do linear regression where you say that y is w transpose x, then what you're essentially saying here, I'm assuming that x includes the bias term as well. What you're essentially saying is that you're trying to fit a line here, right? But in some cases, for example, in this case, maybe a quadratic curve might fit the data better, right? So how do you accomplish that? That is done by doing what we call basis function expansion. And what is basis function expansion? It's nothing but you take each one of your observations. So you have x and y, right? So this is your observation, this is your target. So you replace this with some functional expansions of this. So for example, you can apply 3 functions to this data. Here we are applying one function which is just x to the power 0, this is x to the power 1, this is x to the power 2, right? So now you have a new problem. Now you have x, which has 3 variables, and y, which has 1, and now you learn this line in this 3-dimensional space. And what happens is that if you plot the curve that you get in the original space, it will look like a curve. So that is the idea. Now, the main question that you want to also understand there is that nothing stops you from going further than 2, right? So you can do up to p polynomial expansion, or you can use any other function. You could use a sine of x or sine plus cosine of x. So there's no limit on how many basis functions you can use. And what will happen because of that is that you could actually get a very low training error. You could, in principle, come up with a basis function such that I give you any data and you can learn a curve which perfectly fits your data points, right? But the problem with that is that even though the training error is low, there is an issue of overfitting, which means that this kind of curve might have poor generalizability. And the reason for that is that because this is too complex, right? So I never talked about this VC dimension thing, but there is a measure of complexity of solutions, right? So that's called VC dimension, and the VC dimension of this curve is very high, and VC dimension of a straight line is low. And in statistical learning theory, people have come up with connections between the VC dimension and the generalizability, right? So you want to keep it as low as possible, but you still want nonlinear curves, right? So you need both. So that is why we introduced this notion of regularization, right? So regularization means that you do some basis function expansion, but you try to clamp down on the complexity. So you want smooth curves. You might want, I mean, it's okay to have nonlinear curves, but you don't want curves that look like this, just fitting the data. You want curve that looks like this, smooth, because those have lower complexity. And how do you do that is by doing something called regularization. So we talked about that, right? So you want to understand that part as well, right? But in this problem, I think all we are asking you to do is I'm giving you some data and I'm giving you some candidate weights. So we are not learning from all possible weights here. We are saying, okay, in my bucket, I only have 4 weights and I want to choose the best weight, right? I mean, we have seen a method that lets you choose the best weight from a bucket of infinite weights. That's sort of the gradient descent or the minimization, error minimization formulation. But here I'm saying I only have 4 possible weights and I want to choose the best one. Right? So there is a notion of how to choose the best one. That means that there is a notion of the quality of your solution, right? And you can measure that quality either by the least square error, or you can measure it by assuming that your y is a Gaussian variable, and then you try to maximize the likelihood, right? So that's what you have to do here is, let's say you choose this weight, W1. Oh, you can't see that, sorry. Going on in my own world. All right. So I give you 4 weights, right? And you have to choose the best one. So how would you do that? So let's just look at these 3. So because these 3 do not involve any basis function expansion, right? So the way to do that is that you have some x and this is your y. You assume that your weight is this, right? So when you assume your weight is this, you can now compute the probability of each one of these y's given these x's. So if you remember, right, what linear regression assumes is that y is a normally distributed random variable with the mean W transpose x and some variance sigma square, right? So in this question, I think sigma square is given is given to 0.01. So this is 0.01. Now you also want to be careful about reading the questions. So variance and standard deviation, there is a difference, right? So variance is square of standard deviation, and typically we denote variance by a sigma square, whereas standard deviation is the sigma, right? So you want to be careful when you're reading these things. Anyway, so what you do is, so you're assuming this, right? So let's say assume that W is equal to one of the choices. So 0.30, 0.50. The reason there are 2 is one of them is for the intercept and one of them is for the actual x, right? So now what you can do is you take the first data point, x1, y1, right? x1 is 11 and y1 is 6, okay? And then you append the intercept here. This is the intercept, right? Then you say, okay, we are assuming that y1 is a normally distributed random variable with W transpose x1 comma sigma square. Now you know W, right? W is this, and you know x1, it is 111. So now you can do the inner product. So 0.3 times 1 plus 0.5 times 11, 5.5 sigma square, which is 0.01. So now essentially what you're saying is that y1 is a normally distributed random variable with mean this and variance this, right? So now you can compute the PDF, right? So PDF of a random variable given your mean and standard deviation is just this. EXP. So that's a standard formula. So you know all of these values. You know what your sigma square is. Now this is where I want you to be careful, because if I give you sigma, then you want to square it. But if I give you sigma square, then you just use this value here, right? And you know what the mu is, which is this one, 5.8, and x is x, right? So now you can compute the PDF, the probability of this value. And then you can add it up for all of your data, and you get the likelihood of your data set. Yes. Right, under root 2 pi sigma. Sorry, something happened. Okay, so that's, I'm assuming that makes sense. This is a question about linear Gaussian systems. I told last class that we won't be covering this, so you can ignore it. But if you have questions about it just for the future, please come by and we can talk about it as well. All right, let's move on to next, quiz 8. Quiz 8 is about probabilities and stuff. So this seems to be easy, right? This is basically you have two distributions, right? You have a distribution of normal objects and you have distribution of outliers. So you can think of these as two classes. There's a class A, which semantically means normal objects, and class B, which means outliers, right? And for each distribution, you have probability distributions given, right? So for class normal objects, the distribution looks like this. Now this is a slightly different distribution. So this is not like a parametric distribution in the sense it's not Gaussian or Poisson or Bernoulli or anything. This is a distribution in which you basically specify what are the probabilities for different ranges. So that's another way to specify a distribution, right? So here you're saying that the probability of any data point x to be generated by this class M is x by 16 if the value is between 0 and 4. This half minus x by 16 is between 4 and 8, and 0 otherwise. So it's like a triangle that you're drawing, right? And then the same way the distribution of outliers is uniform, which means that between 0 and 8 it is always 1 by 8, and otherwise it's 0. So it's like a square, right? So these are two distributions. And now what you need to do is basically apply Bayes' rule, right? So you're given a data set in which you have 4 values, 3, 5, 6, 7, and there's a prior probability lambda that a point is an outlier. So that's sort of the probability, the prior probability of the class. So Py is equal to, let's say y is the class label. So y is equal to outlier is 0.4, sorry, 1 by 4, and probability y is equal to normal is 3 by 4, right? So that's sort of the Py equal to 0, y equal to 1. And then you want to compute the log likelihood of the 4 points, okay? So the first question is that we are assuming that all of these 4 points are in the are normal, okay? So which means that it's easy to compute the log likelihood of this data, because if they are normal, that means that you multiply 3, you compute the probability according to this distribution. So if it is 3, which means that it is between 0 and 4, the probability will be 3 by 16, right? It is 5, then it will be here, and 7 also here, 6 also here. So basically you add 1 time of this and 3 times of this, and you get a sort of a total distribution. And you have to be careful because I'm asking you to compute the likelihood of the data set. That means you also have to compute the probability that it is 1, that is y equal to 1, right? So if I ask you to compute the likelihood of just the x's, which is 3, 5, 6, 7, then that's a different question. But if I ask you to compute the log likelihood of the data set, then that is a different question, because there the data includes the x and the y, right? So you need to compute the total probability, and you could do that. So let me just work it out. So this is quiz 8. I think quiz 8. Right? So the idea is this. So you have 4 data points, 3, 5, 6, 7. These are your x's, and your y's are they're all normal. So let's say normal is 1 and anomaly is 0. So outlier is 0. So this is your data. So the probability of this data point will be probability of x to be 3 given y is 1 times probability y equal to 1, right? And then plus probability x equal to 5, y equal to 1, py equal to 1, and so on, right? And you can compute this, because this, you basically look at your distribution. Your distribution looks like a triangle, right? So this is 0 and this is 8. So 3, you will get it from here. 5, 6, 7, you'll get it from here. So you'll substitute those, and y equal to 1 is always 1 minus lambda, right? Because you're given that. So you can compute that log likelihood, and then you take a log of that, you get the log likelihood. Actually, you shouldn't add them, you have to multiply them. I'm sorry about that, because you're computing the joint probability, and then when you take the log of that, then that becomes the log likelihood, right? And then in the question, what they do is they ask you, okay, what if I make one of these, let's say this, instead of 1, I make it 0, right? In that case, when you compute the log likelihood, what will change is that now you, instead of computing this, now you have to compute px equal to 5 given y is an outlier times probability that y is an outlier, right? So in that case, this thing would change. So in every scenario, when we ask you, you essentially change what class you're looking at and the prior as well, and the recomputed likelihood, right? And essentially what we are asking you to do here is try out these different scenarios and tell us which is the best labeling, right? So because if you have 4 data points, you could have 2 power 4 possible labelings, right? You can call all of them outliers, all of them normal, and so on, and you have to figure out which one is the best. So this is like a manual way of doing maximum likelihood estimation, right? And of course, we have seen other algorithms that let you do it sort of in a more mathematical way, but this is just so that you get an idea of what happens, right? So you have some data and you have some possible labelings, and you have to find out which is the best labeling that you get. All right, any questions so far? Yes. So we have to add them all? No, so you compute the probability of each data point, then the joint probability will be the product of these probabilities, right? You assume they're all independent and you multiply them. Yes. Right. So the other one was, if I just gave you x, right, 3, 5, 6, 7, and I asked you what is the likelihood of this data, given we assume that's coming from first only, I mean, so all I give you is one distribution, let's say it is this, and I ask you to compute the likelihood. So then all you would do is, what is the probability of x equal to 3 times x equal to 5, and so on, right? So I think that was the point where a lot of you were getting an error. I mean, right. So this is what, this is the way you interpret it is, what is the probability of x to be 3 given I know it is coming from the normal class, right? And what we have given you here is that for a normal class, for the normal class, the distribution is this. So that's why you use that. All right, okay, let's move on. What was the next one? This seemed to be okay, right? This is basically, you have a data set in which you have 2 variables. So this is your x and this is your target y, and you're trying to learn a classifier which can help you predict the risk or the y, right? And in this case, we were using a logistic regression classifier, okay? And so this is your x, this is your y, and all you needed to do was, in fact, in this one, we were not doing learning actually, we are just saying, I'm giving you a classifier, which means I'm giving you a W, and now you have to find the predictions, right? So all you need to know to solve these kind of problems is that what is logistic regression? Logistic regression is that given a W, you compute W transpose X, right? And then you take a sigmoid of that, right? So you do so logistic regression is you're given X, you're given a Y, and you're given a W. So you compute W transpose X. Now this value will be anything, right? It could be a real, it will be a real number, but then you do sigmoid of this. You compute the sigmoid of this, which is nothing but 1 over 1 plus exp minus W transpose X, right? And this value is guaranteed to be between 0 and 1. So you can now treat it as a probability, right? So what logistic regression says is that P of y to be 1 is given X is equal to this. So if this value is greater than 0.5, then you say it is more likely to be 1. If it's less than 0.5, then you say it's more likely to be 0, right? And then that probability also tells you the confidence. How confident are you in this prediction? So let's say for some data point, you are getting a probability of 0.99. So Py equal to 1 for some x is equal to this. And probability y equal to 1 given some x is 0.52, right? So both of them meet the threshold, right? So both of them, if you are applying that 0.5 threshold, you would say they are both positive points or class 1. But you will have more confidence in this rather than this, right? Here it's almost random, and here it is strongly positive. So sometimes we might ask you to also interpret that, not only put a 0.5 threshold, but also interpret that, all right? So that's kind of the different choices that were there in this problem is, you can count how many mistakes you make by just applying that 0.5 threshold and getting a binary label and seeing how many are not matching. Or you can also look, we can ask you to also look at which gives you the most confident prediction, what gives you the least confident prediction, and so on, all right? Okay, moving on. This one is sort of a giveaway, right? So this is basically just to test your knowledge of deriving these minimization equations, right? So you have to compute the derivative of a given objective function, and then you have to set it to 0, and the answer that you get is the answer, right? And you can refer to the notes that we have from the class or the class video, and I have done it for some of them. So all of them are very similar, right? What you see here is that all of them have the same form. The only thing that is different is maybe the constants, right? And all I want you to do is figure out what effect do the constants make, right? Some of you, in fact, in your programming assignments, some of you used a different constant and lost points, but the answer was correct, so right? But the idea is that the constants do make a difference in your computations, but the eventual performance would be the same, okay? All right, so that's sort of, you can look at this easily. Quiz 9. All right, so what is this about? This is about kernel methods, right? No, this is about, oh, okay, this is about sort of an SVM, right? How do you draw linear boundaries? So all you need to know here is I've give you some data points, right? How do you figure out what is the best margin, right? So you need to understand the notion of a margin. So I think there was some discussion on this, if I remember it right. Let me just go through this little bit. So what I asked you to do in this question was that there are 4 points, 2 of them are negative and 2 of them are positive, right? And instead of actually running a SVM classifier learning mechanism, I wanted you to learn it manually, right? So the idea was, what would be the best margin, right? Now we know that for SVM or any linear classifier, a best line is the line that splits them into 2 parts. But what SVM does, it goes a little further. It says among all the lines that can divide these 4 points into plus and minus, which the best one is the one that has the maximum margin, right? So the one way to do it is, if I give you 4 points, So in this one, what you need to do was to first figure out what would be a margin line. So one possibility could have been that the margin line is the line that goes through the nearest plus, right? The margin line cannot go through this one, because if it is going through this one, then it is misclassifying this point, right? So you go back to your discussion of SVM. So the idea is that you have two types of points, and so this would be the separating hyperplane, and these will be the, on the either side, this symmetric margins. And the idea is that there will be no negative points on this side of the margin and no positive points on this side of the margin, assuming that this is a hard SVM, right? No slack here. So for that, so this could be the only line, and then what you do is you figure out what would be the corresponding margin on the other side. So of course the corresponding margin, if this is the margin, would go through this. Now the thing that you need to understand is that the difference between these two lines is that they will have the same slope because they should be parallel to each other. The only thing that will be different is the intercept, right? So there will be different intercept, and then the final line that you will get, the distinguishing hyperplane, would be right between them, right? So that line would also have the same slope, and the only difference would be that its intercept will be right between these two intercepts. So the way to solve this problem is that you first compute this line, like what is the slope of this line, which is easy to get, right? So you have a line and you know that it passes through this point, right? And you also know that it right. So oh no. So actually you want to force it to pass through both of the positive points. I'm going to assume that it's, so that is one possibility, right? So there could be two margins that you can draw. One is you assume that it is passing through these 2 points, and the second possibility is that you assume it is passing through these 2 points, right? So that would be the best plane. So first you consider this. So now you can compute the slope and intercept of this, because this is a line with 2 points that pass through it, right? So simple geometry. You can compute the c. Then you use the same slope, and then you figure out which of these points will it sort of will the margin pass through, and then you draw that line, you get the c, and then you take a mean of that, and then you will get the c of the actual line. So now you know the actual line as well, right? Then what you do is, of course, the expression for that line would be something like y equal to mx plus c, right? So you know m, you know c, but you need to convert it into this form, w transpose x plus b equal to 0. So you need to rearrange terms here. And then what you do is, then you assume that this is the margin, and then you figure out the equation of the line there. So you get two possible lines, and then what you do, so basically you'll get w1 transpose x plus b1 equal to 0, and w2 transpose x plus b2 equal to 0, right? So this will be the line that you get if you assume that your one margin goes through these 2 points, and this will be the line that you get if you assume the margin goes through these 2 points. Now you have to select which one is better, right? So to do that, you compute the margin, right? Because in SVM, what we do is we assume that we maximize, right? We maximize 2 over sigma square, or which is equal to 2 over w transpose w, right? So you compute 2 over w, so you compute 2 over w1 transpose w1 and 2 over w2 transpose w2, and whichever is higher, you choose that one, right? So this is a manual way of finding the best hyperplane, but of course this you could do because you only have 4 points, so there are not too many possibilities, but in general we use our dual optimization and all that framework. Any questions here? So I mean, I'm sure you have solved it already, but if you've not, please go through the steps and you'll find the answer. This one is pretty easy. This one is just, you have a bunch of points and I give you a kernel function, right? So here all you need to understand, sorry about that. So this problem. So here we are talking about kernel transformation, right? So the idea is that we have some kernel function, and well, actually here we have some basis function expansion. and then we want to convert our data, which is in two-dimensional space, into this new space and compute the similarity in that space. So here the idea is that you have all these data points, right? So 8 data points, and you have this transformation where you, so this is x, this is y. This is a little misleading because here we are assuming one of the variable is called x, one of the variable is called y. So just be careful there. But all you're saying is that if you have x and y, you convert it into this three-dimensional space. So this becomes 1, 2, 4, and 2. So this is 1, square of 1, square of 2, and 1 times 2, 4, right? So now you convert data into this new space, and then you compute the similarity by applying a dot product. All right. So and then eventually you want to just compute, okay, which ones are the closest. So for example, so the idea would be that kernel functions, right? So I'm giving you one data point, let's say, that is 1 comma 2, right? And the kernel function that we are applying, well, in this case we are actually doing the expansion. So we are converting this into x square y square xy, which means that this becomes 1, 4, and 2. So now suddenly this data point is in three-dimensional space. Same way, if you take data point 1 minus 2, that becomes 1, 4, and minus 2, right? Minus 1 and 2 becomes 1, 4, and minus 2, right? So same way you can expand all of the 8 points. Now what we wanted you to do is compute the similarity between each point. The similarity between these two will be a dot product of these two. So dot product is essentially 1 plus 16 plus minus 4, right? So that's 13, right? Dot product between these two will be something else, and so on. And then you have to say which one are the closest, right? So the trick here is that even though in the original space, maybe this was closer to this one, but in the transformed space, the similarities would change. So you just need to know how to compute these operations. Any questions on this one? All right. Because you're computing a similarity, so it depends on what you're asking, right? So here they're asking, for example, the most similar. So you take the one that's highest because this is a similarity function, right? So higher value means more similar. But if it's a distance function, then it's opposite. Higher means you're far away. Okay, 10. That's a similar question, right? Oh, I see. The last question actually was the different one. Here it's different. This is the one that I explained to you earlier, right? Where you had to draw two possible margins and figure out which one is better. The other one was more about if you, so let's say if I compute my hyperplane to go through this, I can rotate it little by little and see which one gives you the best answer. So that's fairly straightforward. I don't know if anyone has a question about that one. All right, so and we can discuss it over Piazza as well. This one is about support vector machines again. So I've given you a bunch of data points. So this is like data in two-dimensional space, but it is very beautifully distributed. So it's distributed on a grid, but it is essentially a data, right? And what you need to do is draw a line. And what you can see here is that I don't think you can draw a line that perfectly separates the two. So this is not a separable data set, linearly separable data set. So you have to draw a line, and there will be some misclassification, and you have to figure out the line which gives you the least misclassification, so least slack, right? And that is what the soft margin SVM does, right? So I think this one, all you need to do is compute the slack. So if you go to the slides, right, we have a formula for the slack. The slack is essentially how far you are away, how far are you on the wrong side of the margin, right? So if this is your margin, this is your line, these are your margins. If you have a data point which is on this side, so this is a positive data side. So this one has a positive slack because this is how far it is from from the margin, right? So you want to know how to compute this, and this you can compute by just doing a dot product. So refer to the slides, but essentially what you do is for a given line. So here what you do is, here what we have given you is we have given you a line actually. So you need to know how to draw this line here, which is easy. So once you draw the line, then you can check which ones are on the wrong side of the margin, and then you can see how much slack is there for each one of them. All right. So for example, here it says the slack for the correct answer is slack for 5,6 is 0, because what would have happened is if you had drawn the line here, you would have seen that the 5, 6 is on the right side of the margin. So no issue there. But the slack for, let's say, 1,4 is 2, which means that this point would be on the wrong side of the margin, and you could compute how much the slack is. The reason they are on the grid is because that makes computing all those slacks very easy. Okay? Yes. When you say the slack for 5,6, do you mean like point on the line? No, it's on the right side of the correct side of the line. So it could be on the line as well. So the definition of slack is that if you are on the correct side of the margin, then there is no slack. It doesn't matter how far you are away from the margin, right? But if you're on this side, then you add, then you consider it. This one is about k-means. So here, to solve the k-means problem, one thing you need to understand is what is k-means, right? So there is a notion of a centroid, which are the representative points for your clusters. And then in each step, what you're doing is, given centroids, you're assigning rest of the data to the centroid. So each data goes to one of the centroids, depending on which one is closer. And then once you do that, in the next step, you recompute your centroids, because now you have a bunch of data points, and then you compute the average of those, and that becomes your new centroid. And then you keep doing that until your centroids stop moving, all right? So for example, in this case, right, what will happen is that these are your two centroids, and these are basically a bunch of your data. Okay, so there are a lot of data points here. I think you're assuming that they are uniformly sort of distributed here and uniformly distributed here. Now what happens is, in the first step of k-means, right, what will happen is that some of the points, whichever are closer to this point, will say this point is our savior, and some others will say this one. Now depending on what these distances are, I think they are given, so you can really compute. So I think what will happen is that all of these might, I think, will call this one as their centroid, and all of these will call this one as their centroid. So then in the next step, you will compute a new centroid, and that will just become this, right? Because that's the actual centroid, and this will become this, and after that nothing will change. So that is the idea behind k-means. And then essentially all the questions that could come on k-means would just be you simulating the algorithm on some given data, all right? And yeah, so for example, this one, right? So this one, I think a lot of you had questions, and this one is also I mean, actually it's not too hard to understand. So the idea is that you have three clumps of points. So there are a bunch of points in A, a bunch of points in B, a bunch of points in C, right? And then the initial centroids you could pick from any one of these, right? So as I said, I think if you refer to the video of one of the classes, I sort of went through this, and somebody had posted that. So I don't want to repeat it, but the idea is that there are 27 possible ways you can choose the initial centroids, right? You can choose all three from here, all three from here, all three from here, and other combinations. And then for each one of them, you will have a different outcome, right? So if all three centroids come from here, then as k-means progresses, right, one of them would sort of move here, but then after that, the other two will stay here. So which means that will be the outcome. So you can figure out different outcomes. So for example, if each centroid comes from A, B, and C, then this would give you a perfect output, right? After some point, a couple of iterations, there will be a centroid right in the middle of this, there will be a centroid right here and centroid right here, and the system will stabilize, right? So that's, you need to figure out for each one of these possibilities what happens, and then you can compute the probability of getting the right answer in each case. So refer to the video, I think that will make it clear. Last one, EM, right? So this is I'm still trying to figure out how to really give this for your and the exam, because I think here you were using a code to run this, but you could probably do it by hand as well, right? So there are two steps in EM for a Gaussian mixture model, right? So there is a step E step in which you have to compute the responsibility of each data point to go to each one of the mixture components. We call it RIK, and there's a formula to do that, right? So if you refer to the I don't even remember what it was, part E5 Beamer. Right. So refer to the E2 slides, and here we have sort of these equations. So there's a E step in which you compute for every data point that is denoted by I, and for every mixture component that is K, you have to compute these values given your current estimate of theta, which is your parameters. And in the M step, you recompute your parameters using what your RIK is that you computed in the E step, right? So these are two specific sort of steps that you need to follow, and all you need to do in these two problems is basically just fit those values in, right? So you need to know how to compute the PDF of a Gaussian distribution, and after that, because that is what you will use here, right? The P is just the PDF of X, or the probability of X given one of the distributions which are assumed to be Gaussian, and that's it. That's what you do. This one is about PCA. I think PCA is standard, right? So you have some data set X, and the way to do PCA is that you first compute the covariance matrix of X, right? In this case, I already gave you the covariance matrix. Then you need to do the eigenvector decomposition of this. So which means that obviously it's not, I mean, you can do this by hand, but I won't ask you to do that. But so in general, we will probably give you the eigenvectors. So all you need to understand is that what happens, how do you go from X, which is your data in your original d-dimensional space, to Z, which is your data in a lower dimensional space. And that is done by multiplying X by some number of eigenvectors, right? And the way you choose the eigenvectors is also important, right? So you can choose eigenvector, you have to choose the eigenvectors with the largest eigenvalue, because that guarantees the maximum covariance coverage. All right, and then I don't think there are questions about spectral clustering, because we talked about it towards the end, and also SVD. So I'll try to post a couple of questions, practice questions around it. But the idea there is also simple. You need to know the algorithm, how it works, and what we could ask you is, if I give you some data, how would you run that algorithm on that, right? So yeah, that's it. Any questions so far? Yes. Right. Right. Yeah, I mean, so you have to be careful there, right? So there are two formulas for PDF. One is if it is of a normal distribution. One is if it is a univariate distribution. Then it looks like 1 over under root 2 pi sigma, small sigma exp minus 1 by 2 sigma square x minus mu, right? X minus mu square. But if it is a multivariate distribution, for example, in this data set, right? In this data set, oh, well, this one is univariate, right? So this is fine. But if I give you a two-dimensional distribution, then you have to use the multivariate Gaussian formula, which has the x minus mu transpose sigma inverse x minus mu. Right, where you have a covariance matrix. Because when you have a multidimensional Gaussian variable, then you have a covariance matrix. But if you have a single variable, then you have a variance. That's a small sigma square. Any other questions?